So let's knock out those slides. So if you turn to the slides, we'll do the whole chapter 19 thing. So this actually is a picture of a radio telescope, part of a radio telescope. Remember the whole idea of interferometry, because radio wavelengths are so darn long. So that's actually working together with multiple dishes. So some of the stuff I don't have to spend much time on, because astrobiology, oh my gosh, how many times did they say astrobiology in the video we just watched? Okay, so but honestly, they spent some time, when you're into looking at what sort of life might be beyond Earth, basically you start with life on Earth and try to understand how it behaves or how it came about, and then apply that to beyond Earth. So astrobiologists have to figure out where they might find other life outside of the Earth, and then also look for evidence. So how unique is the Earth with regard to life forming? So some of the stuff the video touched on, the whole idea of how do we study past life using fossils, and actually we can use the whole process of sedimentation. For example, you're looking at the Grand Canyon right there. If you were to go back to the bottom layer of the Grand Canyon, you're looking at about 500 million years worth of the Earth's history, which still doesn't get us to the 3.5 or 3.85 billion years that we believe that long ago that life started. These little things right down here, okay, I got so excited when I didn't realize that video must have been like 2007 or something, but this actually were the little stratometeorites or whatever that gal was looking for. Okay, so right. So with regard to Earth, or with regard to life forming on Earth, we had some what do you call it we had some lucky cards, I guess you could call it. So for instance, well, I don't know if you necessarily call this a lucky card, but life couldn't develop until till our solar system kind of settled down. The period of heavy bombardment that we see evidence on for the moon and such, that that stopped about 3.9 billion years ago. So about 3.85 billion years ago, we could first see the little single cells of life that first formed in the oceans. Speaking of oceans, we needed to have them before life could begin. So you need to have it cool down enough to begin our water cycle, our hydrological cycle. The video talked about ultimately oxygen coming from photosynthesis, green plants and such. So that actually is a figure from your textbook of one of the earliest green plants that started populating Earth's atmosphere with oxygen. If you read your textbook, I think it's interesting that actually up to, I don't know, 2 billion years ago maybe, oxygen was toxic to those life forms that were just forming. So, all right, geological activity, the video kind of talked about we needed plate tectonics in order for life to be sustained. So, kind of from left to right, the left you see a DNA strand, okay? Now there is a theory of evolution by natural selection as first stated by Darwin, the naturalist. But, and your textbook emphasizes this, the theory of evolution. It's kind of like, for those of you who've studied chemistry, the atomic theory, the theory of atoms. The theory of atoms, the idea that what we talked about an atom is made up of a nucleus with protons and neutrons and electrons around it. You know, if you talk to chemists, if you talk to probably a middle schooler, they are not going to argue atomic theory, the theory of atoms with you. The theory of evolution has undergone the same scrutiny as the atomic theory. So what it means by natural selection is basically it's the survival of the fittest sort of thing, that there can be mutations in DNA strand that results in an evolutionary sort of process. If that new trait or characteristic is positive, then that will be the individual that survives and gives root to offspring. So that's kind of how evolution goes about. There's an evolutionary tree over there on your far right. Basically, the DNA kind of branched off to bacteria, archaea, and then there's the animal and plants over there on the left. So, of course, the way you read this evolutionary tree is up here. This is stuff we still have, and it all came from one common sort of organism. So from chemistry to biology, the video kind of talked about if you had the right, you can have the right chemicals. They mentioned near volcano vents in the bottoms of oceans. You have the water, you have the chemicals, and you have a heat source. Okay, then you can have possibly over time the basic building blocks of life form, and then those building blocks assemble into life. This is funny. As I was preparing for today's lecture, I actually posted this little guy on my Facebook page maybe, I don't know, 3 weeks ago. But that actually is an organism, I don't know if you call it an organism or a little animal, here on Earth. It's a type of extremophile in that actually this little critter can survive the vacuum of space. Okay? So one of the things with regard to building blocks, we said where do the building blocks come from? They can come from the Earth itself or meteorites, comets, that sort of things, you know, depositing on the Earth. As far as life itself, and your textbook kind of puts it as the terrestrial planets have been swapping material. I don't know how they put it. I just think it's kind of funny. But we know that we have meteorites that actually came from Mars, okay? And I imagine Earth meteorites landed on Mars, okay? So in that way, we could actually have life have been deposited that started elsewhere. So I think that's kind of cool. So this is kind of emphasizing the whole, if you're into dinosaurs, I know it's hard for you to see. You see the Triassic period, the Jurassic period, and all that. Maybe kind of recognize these as kind of the age of the animals, okay? But notice that actually this age is just a small little sliver right here in the time frame that the Earth has been an Earth. So I don't know if you can see it very well, but this little thing over here, Earth forms right over there. Okay, let's see. This is carbon evidence of life. This is evidence of kind of those little gizmos we saw a picture of. This is oxygen in the atmosphere. So, I mean, that's quite a bit of time. Buildup of oxygen, okay. Then this actually is all down here, okay. So my point is life, you know, the animals, and then ultimately over here, I think the Quaternary period, that's where we are. Hominids appear clear over here. So we are just a blip on kind of the overall chain of life, okay? So when we look for life, smart life, intelligent life on other planets, we have to account for this. How long did it take for us to get where we are with regard to the process of evolution? So life in our solar system, things that we're looking for, we need to have some sort of matter, okay, atoms. We need to have a source of energy, which is, those are, you can come by those, especially if you go to a planet or a moon of a planet. But what's hard to find within our solar system, we're not sure about planets extrasolar or exoplanets, is liquid water. Okay, so that is the tough place, the tough thing to find. Actually, the thing I gave you, the sheet that says Unit 6, one of the terms, the first term, I believe, is basic requirements. So that must make it to your final in some form or another. So candidates for finding those three, meeting those three requirements, of course, the video talked about Mars. It talked about Europa. Actually, Ganymede and Callisto also have kind of that crusty ice and probably liquid underneath it. It didn't talk about Enceladus, but it did talk about Titan with a liquid methane cycle. That's pretty cool. All right, so that was life in our solar system. What about life around other stars? Well, your book prefaces this whole discussion with, when we're talking about life around other stars, we're not going to send a probe there like we sent to Mars to basically dig down and scoop up a piece of that planet. Okay, so we are only limited to surface life. That's our best bet. So good candidates to have life, those exoplanets or moons around exoplanets. For instance, the planet needs to be in the habitable zone. Okay, that was where basically it can sustain liquid water. And this down here, this figure down here, that green is the habitable zones. Now, there are different habitable zones depending upon the type of star, the amount of energy that that star is putting out. It makes sense to me, too. Your textbook says, but hey, as far as habitable zones go, Earth's moon is in the habitable zone. It's in the green zone. But Earth's moon doesn't have this other stuff. Okay? So also, in order to sustain life or for life to evolve as we understand it, it needs to have active volcanism, where basically the gases from the center of the planet come out and are gravitationally held to form an atmosphere. It needs to have plate tectonics. That's the second of three. And the last is it needs to, remember how Mars lost its magnetosphere? Okay, it needs to have a magnetosphere. And remember, it can only have a magnetic field if it's kind of ooey-gooey in the center. So those three actually, to me, all deal with the size, how large the planet is. Also, how close it is to the star. Okay. So kind of back to the Earth. What makes the Earth unique? Are there other criteria other than those four that we should be looking for or looking at? Okay. So with regard to the Earth, one of the things, and this is probably kind of controversial from what I read in your textbook, is our sun's location in the Milky Way galaxy. On your unit exam, you guys probably told me that we are actually about 27,000 light years from the center of our galaxy, so we're kind of halfway. The thing is, if you're too close to the center of the galaxy, then actually it's too active and you have a lot of starbursts and you can have quasars that can like totally I don't know about quasars, but you can have supernovas that can sterilize you. That's bad. But if you're too far out, then actually you don't have much stars being born and you don't have the heavy metals being created. So there actually is kind of a sweet spot to your position in the galaxy. The other thing is planet shielding. So remember we talked about how Jupiter was kind of a big brother to us, kind of kept our backs as far as kind of the heavy bombardment period. The other thing is a moon, our satellite. Earth, remember, kind of has an anomalously large moon, okay, but we think that Earth's moon actually is a part of the Earth because Earth got hit early on. And part of the Earth splashed out and created its own little moon. But that moon has been good for a number of reasons, and maybe this has been a while back, and I don't think I read it in your textbook, but if the moon creating tides, our ocean's tides, actually that was a requirement for life to stir and be created in our oceans. But the other thing your textbook talks about is the moon helps to kind of stabilize our twisting each day, our rotation. So yeah, the video we watched did not quite have the whole Kepler thing down. Kepler was a success. Okay, the spacecraft that was put into orbit about the Earth, the Kepler telescope, was definitely a success to finding all sorts of planets in orbit about other stars. And I think we talked earlier that most stars have planets. We're limiting ourselves just to the terrestrial planets because the Jovian planets would not be a good one for life to begin on either. Okay. So how do we detect life on other planets? Now this caught my eye, and I had to read it a few times from your textbook. But here's the deal. They're actually saying that there could be more advancements in telescopes. Now, this would be a telescope like the Hubble Space Telescope that orbits the Earth, but telescopes that actually could look at these planets in orbit about other stars and see continents and oceans. Okay, so I don't know. I think that just totally amazes me. But the other thing that video actually did talk about was looking for the presence of gases that in the atmospheres of other planets. So, I mean, it's like, it really makes sense. If you see oxygen, like the guy said, you're like, oh, well, maybe it actually could be life creating that oxygen, or carbon dioxide, life creating that carbon dioxide. Or we could have all some sort of other different sort of chemistry with this life. Okay, so what you're looking at here is actually, if you were on another star, kind of looking back at the planet Mars, okay, you would see the presence, the fingerprint of carbon dioxide. Looking at Earth, the fingerprint of carbon dioxide, water, and ozone. Looking at Venus, the signature of sulfuric acid and carbon dioxide. So these are just examples of what you can, and look at, this is infrared spectrophotometry. Okay. All right, then I liked what the guy said. A lot of my astrobiology friends are just looking for dumb life. He wants to look for smart life. So SETI, you might have heard about it. It's been around for, I think he said, 60 years. Search for extraterrestrial intelligence, and actually that was he was with the SETI Institute, the guy that we saw. But just SETI in general is looking for intelligent life out there. So like I said, why do we care about finding little microbes on Mars? Well, if we find little microbes on Mars, which I do think we're going to find sometime, then where the odds are better for having life elsewhere. You know, we're not going to find intelligent life here on Mars or Enceladus or anything like that. Okay, but where do we find microbes? So SETI is actually looking for a signature. And remember how he said that our rate, by the way, when we transmit a radio signal, okay, that information travels at the speed of light, because radio is an electromagnetic radiation. It's like a cousin of light. And so he said, basically, if we have been transmitting for 60 years, which is not very long, radio signals, basically somebody, a civilization that is 30 light years from us, could have received it and sent something back. It's kind of like 30 years there, 30 years here. That's 60 years, right? So, I don't know. It's interesting. So the Drake equation, I'm going to show you a version of the Drake equation I got off the internet, which is a little different than the Drake equation in your textbook, but it's similar enough. But right there is Dr. Drake. I assume he's doctor. And basically the Drake equation is more of kind of like a thought to start to get you thinking with regard to our Milky Way galaxy. How many civilizations, intelligent civilizations, do we think we should be receiving a signal from? And that's clear over on the left. That's the value of n. Okay. So n is within our Milky Way galaxy, the number of civilizations that we should be able to communicate with. R is considering how many stars are forming in our galaxy. The next term is the fraction of stars that have planets. The next term is the average number of planets that can support life. The next term is, can you get up please? Thank you. The next term is the fraction that can continue to support life, not just initiate it, but continue to support life. That F sub I is the fraction that can support intelligent life. And then the next one is the civilizations that can go ahead and develop the technology to communicate, to send and receive communications. Now the L is a sad term. Actually, the significance of L is how long do these civilizations last? And there are folks out there that would say our civilization is at some point probably going to wind down. We're going to self-destruct because we don't like each other very much. We don't like each other. And we aren't taking care of probably what needs to be taken care of. So, yeah, that's probably what's going to happen. But, so that is a factor in, if they're smart enough, how long will they live? So, all right. So, as I mentioned, SETI uses a lot of radio telescopes. Okay. let's see, but the problem is let's just say, and your textbook talks about this, that we send a signal and we want somebody that is 30 light years, civilization is 30 light years away to receive our radio signal. Well, that radio signal is diluted out the square of the distance it goes. So that's a tough thing. In 1974, actually, we transmitted this radio signal to a cluster, a globular cluster. Remember we talked about Messier objects? Actually, Messier object number 13 is a globular cluster in Hercules. And so your textbook says, why that? Why M13? Why do we think life might be there and we're sending it that way? And the answer is that they have a fair number of stars that we think would have planets that might have civilizations that would fit the bill. So we're crossing our fingers, right? 25,000 light years away. So I have a few slides. Well, what about travel between stars? I mean, I'm talking about us traveling between stars. Well, with regard to humans, part of humans right now activity going between stars, the best we can say is that we have several spacecraft that are in the process or have left our solar system. Okay, so our solar system is basically the sun, the planets. Remember, we have the Kuiper belt and we have the Oort cloud, right? And basically, then you can leave our solar system. I think it's Voyager 2 or Voyager 1 that is a big hairy deal, has left the solar system. Pioneer 1 and Pioneer 2. Now, these 4 spacecraft, as I understand it, are still sending signals back home. So that's pretty cool. Okay.
So they haven't gotten sucked into it.
No, they're just, and according to Newton's laws of motion, actually, they're just going to scoot along down the road.
They're just chilling.
They are. Now, not the Pioneer missions, but the Voyager missions. I guess the Pioneer too. So this is something that was in the Pioneer mission, and this is something that actually was in the Voyager mission. So they're like a message in a bottle sort of thing. Go on. So the nearest star is Proxima Centauri. So traveling at the speed they are, which they should because nothing's going to stop them, it's going to take another 100,000 years for them to reach the nearest star.
Oh, we're going to be gone by then.
So, yeah. I hope generations of humans are still around, but... Okay, so those are spacecraft traveling outside of our solar system. What about people? Well, it gets problematic, as you might imagine. Because if those spacecraft are traveling at what, 1/10,000th speed of light or something like that I had on my slide. So if we want it to be practical at all, we need to push ourselves to traveling almost the speed of light. Yeah, I know. You're like, really? And if we're going to do that, and actually this is on your test, it's another term. If we're going to do that, we need to find a new way to power our spacecraft other than just burning rocket fuel, basically. Okay? So there are 3 things down here, okay, ways of, and actually these are proposed in your textbook, alternate methods of propelling our spacecraft. This one, this one here, actually was put forth in 1960. Basically, you go out and you get your spacecraft in outer space, and then you have a series of thermonuclear explosions that basically, and they propel your spacecraft. So of course you don't want your spacecraft to be hurt, so you kind of have this like little propelling little cap there. The next one is basically, we talked about how explosive matter and antimatter are when they meet. Okay, so that's all kind of, I don't know if that's really going to work. But the third one's kind of cool up there. Basically, nuclear fusion, of course, releases energy, and there's a bunch of hydrogen in outer space. I say a bunch, but not really. Outer space is mostly no atoms. So what you do is you have this humongous scoop right here that is gathering hydrogen atoms. But there's not very many hydrogen atoms we have. So it has to be about the size of a planet to look for hydrogen atoms so it can come and do nuclear fusion on them. So that's kind of tricky. Too bad it's not like Star Trek where you can go faster than the speed of light sort of thing. This also says while you're traveling so fast, 90% of the speed of light, The problem is that particles, subatomic particles, radiation particles actually would be very dangerous, so you'd have to come up with new shielding for your spacecraft too. Makes sense? All right. The last slide, okay? And the video did not address this, but aliens, are they out there? Okay. The Drake equation, although I didn't come up with numbers to kind of, put in there, the Drake equation would suggest that there are a fair number of civilizations in our galaxy that should be technologically advanced, even more advanced than we are. If you read your textbook, they kind of talk you through why would they be more advanced than us. Well, they just probably got more of a head start. We haven't been, our sun hasn't been what it is for as long as some stars have been what they are. Okay, so if that's the case, okay, they should already, aliens, other civilizations should already be just kind of scooting around the Milky Way galaxy. They should be galactic travelers, okay? They should be. So Fermi's paradox goes something like this. Basically, there's a fair bit of evidence, putting the pieces together, that it's quite plausible that there should be aliens traveling throughout our galaxy, but we don't see them. That's the paradox. There should be, but we don't see them. So what's up? So possible solutions that your textbook talked about, possible solutions to this paradox go something like this. The first one is, they aren't out there. We are alone. Okay? And that would be to say, if we are alone, the only reason could be that the conditions we talked about earlier don't exist anywhere else in our galaxy. Nowhere else in our galaxy do they have all those conditions, which that's probably not likely. The other one is very sad, that actually there were alien civilizations that developed, okay, but either the means of getting between stars was not practical. Remember those 3 ways I told you why we can get between stars? That didn't pan out. There's no way to get between stars. Or they're just not curious enough. I suppose that could be possible. But the saddest, I think, is the third one, that actually they advanced to a certain point, and then they just, technologically, they were going along just at a fine clip, and they basically annihilated their civilization. Okay, so they either have to start from scratch or they didn't get a second chance. Okay, the last one is kind of scary too, and actually Stephen Hawking was noted 1.5 years, 2 years ago of saying something like, if there are aliens out there, I'm kind of scared to see them. Okay, because if there are aliens out there, a third solution would be that there are aliens, but they just have not revealed themselves to us. And you have to think, why would they not reveal themselves to us? It could be like the guy said, we are ants to them. Okay, it could be they just don't want to, that sort of thing. So those are 3 solutions to Fermi's paradox.
It would be like ants and humongous.
What's that?
Is it more like ants are they humongous, or would